Hi everybody, this is my implementation for MPPI control for agile unmanned aerial vehicles, and I try to obtain the high-speed trajectory tracking results outlined in the paper as part of my final project implementation in the course Mobile Robotics at Northeastern University, Boston in spring 2025. So this is a top-level overview of my results obtained for three candidate trajectories, especially figure eight, circle, and slanted circle. This shows the tracking is being done without fail across all three trajectories with tuned cost parameters and a simulator that I built myself in Python. Um, the graphs outlined below, I will go into detail in the next slides. So going to the first trajectory, figure eight, we have a drone that's trying to loop a eight-shaped trajectory, and our MPPI initially, when I was building out the simulator and building out the control algorithm, I was unable to track more than three loops effectively. So what I did was that I implemented a low-level controller that would augment the thrust and placed more control reward for staying close to the loop, and or made my cost functions basically try motivated more to stay around the loop. I was now this loop tracking is very robust and it can keep on looping indefinitely. I have stopped simulation at 8,000 steps roughly for all the three trajectories, and here you can see in the graphs on the screen. In the last graph on your right side of the screen, you can see that the position tracking error is actually really good. It mostly stays below zero point 0.6 meters. And in the second graph, you can see that the drone morale stays above the commanded reference, which says about the thrust augmentation that is being done with the PID, up in addition to whatever is being outputted by the MPPI. And moving on, this is a slanted circle. It's a special trajectory because the thrust has to be constantly changing to loop around the candidate trajectory. And you can see on the screen that the speed that I'm able to achieve is around 9.5 kilometers per hour. Uh, and it is not that much compared to what they've got in the paper of 44 kilometers per hour across all three trajectories. But something that I understood was that when you have to keep changing your thrust constantly, it's very hard for the drone to keep a high speed and also achieve efficient tracking. And going to the graphs, you can see that the position tracking error on the bottom of your screen, bottom right of your screen, is actually really good compared to figure eight because I stay below zero point 0.4 meters of tracking error. And in the second graph, I am able to track the reference almost perfectly, apart from the peaks, and it tracks it uh, very well. And moving to circle, this is a little different experiment that I did after working with figure eight and standard circle. Actually, I received the similar result as previous trajectories for this as well, but I wanted to see how fast the drone can loop around the circle and not lose tracking. And basically, I had a lot of issue with initial experiments where the drone would just spiral off into space after doing through three loops, and I tried to combat that here by adding more weight towards staying on the loop in the cost functions. Um, and I also added a new term, progressive reward, for all the three trajectories mentioned. Basically, that would give more importance to a rollout that was closer to the candidate reference state. Uh, I use all analytical functions to generate a reference state and slice the reference trajectory, computed reference trajectories to the controller to compare itself as a baseline and choose the best rollout. Uh, and in the graphs on your screen, in this, I also achieve really good tracking where I stay within the required region, and also the commanded thrust is really good because I stay above the reference given in this circle, and that goes on to say how robust the thrust augmentation is going on in addition to MPPI and PID. And if you guys want to see how you can use this, I have uploaded the code as an IPYNB file that anybody can run on the system. Uh, It's very system agnostic. You don't need a CUDA or anything. I have developed all this on an Apple M2 MacBook. So anybody can run this on their system and play around with the cost functions and see if you can add more obstacles, which is my next plan. I plan to add a little more obstacles in the scene, in the candidate trajectories, and keep the same speeds and try not to change the cost functions parameters and see how much of a reverse tracking I can achieve. And the next step after that would be to use um, this knowledge and try to implement it on a real-time system, as that the sim to real would be the hardest challenge, and that's something that excites me. Thank you very much for listening to this talk, and have a good day.